Hello everyone, this is Dr. A classes for BTech students. Today we are going to explore metamorphic rocks. Rocks that get completely transformed deep underground by heat, pressure and chemical fluids. As part of the rock cycle, they illustrate how Earth's material are continuously altered over time. In engineering geology, metamorphic rocks are crucial to understand as their composition, texture, and structure offer valuable information about material strength, deformation patterns, and the suitability of sites for stable and long lasting construction. Learning objectives of the course is defining metamorphism and the formation process of metamorphic rocks, describing the various types, structures, and texture of metamorphic rocks, identifying major metamorphic rock types based on composition and appearance, understanding the engineering significance and practical use of metamorphic rocks in civil construction, differentiating metamorphic rocks from igneous and sedimentary rocks based on their origin and characteristics, interpreting metamorphic structures such as foliation and lineation, and their relevance to engineering site assessment. What are metamorphic rocks? The term metamorphic comes from meta meaning change and morph meaning rocks that have undergone a significant transformation in their structure or composition. Metamorphic rocks are derived from pre-existing country rocks known as protoliths or country rocks, which may be igneous, sedimentary or even older metamorphic rocks that have undergone mineralogical, textural and structural transformation under the influence of heat, pressure and chemically active fluids without melting it. The diagram illustrates how country rock is altered during metamorphism. Heat from deep within the earth, high pressure from overlying layers, and tectonic forces, and the infiltration of chemically active fluids cause mineral changes and the development of new texture. The transition zone marks the gradual change from less altered rock to fully metamorphosed rock, producing structures such as granular texture. At deeper levels, pre-existing metamorphic rocks may be present, some of what have undergone multiple metamorphic events. What is metamorphism? Metamorphism is the solid state transformation of pre-existing rocks due to changes in temperature, pressure, and chemical environment without melting. Unlike surface processes like weathering and diagenesis, metamorphism takes place deep within the earth, where rocks are subjected to elevated temperature, pressure, and chemically active fluids. These conditions cause significant changes in the mineral composition, texture, and internal structure of rock without melting it. This process results in formation of new rocks with different physical and mechanical properties which are critical for understanding geological behavior and engineering suitability. The image shows a metamorphic rock displaying distinct foliation formed under the influence of heat from above and directed pressure from both sides, illustrating the solid state transformation of pre-existing rock. Agents of metamorphism. Metamorphism is driven by three primary agents that transform pre-existing rocks without melting them. Heat increases the speed of chemical reactions and causes minerals to recrystallize into more stable form. Pressure includes both the weight of the overlying rock and the directed force of tectonic events. This pressure can cause minerals to reorient, creating a layered texture known as foliation. Chemically active fluids, hot iron-rich fluids that circulate through the rock. These fluids accelerate chemical reactions and can transport materials leading to the growth of new minerals. Understanding these processes help assess rock stability, strength, and suitability for construction in areas like tunnels, dams, and foundations. The diagram shows how heat, pressure, and fluid act together to convert a pre-existing rock into a metamorphic rock through the metamorphic process. Types of metamorphism. Metamorphism is categorized based on the dominant geological condition that caused the transformation. Thermal or contact metamorphism, caused primarily by heat from intrusive magma bodies. Dynamic or cataclastic metamorphism, resulting from mechanical deformation along faults or shear zones. Regional or dynamothermal metamorphism, due to both pressure and temperature over large areas, typically during mountain building. Plutonic metamorphism occurs deep within the Earth's crust under high pressure and temperature but without significant deformation. Metasomatism involves chemical alteration of rocks by fluids leading to changes in mineral composition. Shock metamorphism, triggered by meteorite impact, creates unique structures like shatter cones and high pressure minerals. Thermal or contact metamorphism. The rock shown in the image represents thermal or contact metamorphism, where country rocks has been altered by intense heat from nearby molten magma. Thermal or contact metamorphism occurs when country rocks are baked by the intense heat from nearby magma intrusions such as silts, dikes, or batholiths. This baking effect causes changes in the mineral structure of the surrounding rocks without significant pressure or deformation. Since the pressure is relatively low and there is little to no tectonic stress, the resulting rocks do not develop foliation. Instead, produces non-foliated rocks like hornfels, cordite, and marble. The type of rock produced depends on the composition of original or the parent rock. The changes mostly occurs in narrow metamorphic areal, which is the zone around the magma intrusion where the heat is most intense. The main process at work here is recrystallization, where existing minerals grow larger or new high temperature minerals form, all without melting. This type of metamorphism is very common around igneous intrusions like silts, dikes, and batholiths. Dynamic or cataclastic metamorphism. The rock shown is produced by dynamic or cataclastic metamorphism characterized by crushed and elongated mineral grains along a fault zone, formed under intense directed pressure and shearing stress. Dynamic metamorphism occurs mainly along fault zones, shear zones, or tectonic plate boundaries where rocks experience intense mechanical stress. In these zones, rocks are not altered by heat but by mechanical deformation due to tectonic forces. Under such conditions, rocks are crushed, broken, and ground down into finer materials. The temperature is typically low to moderate, but the pressure is high and directional, often related to large-scale movements of the Earth's crust. As a result, rocks like fault breccia, myelinite, and pseudo-tachylite formed by frictional melting during faulting are produced. These rocks show signs of grain size reduction and minerals may become aligned along foliation planes due to the directional stress. This type of metamorphism highlights the role of mechanical energy in altering rock structure and texture even when thermal effects are limited. Regional or dynamothermal metamorphism. The rock shown is produced by regional metamorphism displaying distinct foliation and altering dark and light mineral bands formed under high temperature and directed pressure. Regional metamorphism is the most widespread type of metamorphism affecting large regions of the Earth's crust. It typically occurs during mountain building events where rocks are subjected to high pressure and temperature over a broad area. This process involves the deep burial of rocks under thick accumulation of overlying materials along with compressional stress and tectonic deformation. As a result, rocks are squeezed, folded, and chemically altered over time. Due to high directional pressure, regional metamorphism commonly produces foliated metamorphic rocks such as slate, fine-grained from shale, phyllite, slightly coarser with a silky sheen, schist, medium to coarse-grained rich in mica, gneiss, banded high-grade metamorphic rocks. As pressure and temperature increases progressively, rock undergo mineral recrystallization, the formation of new metamorphic minerals, and textile changes, a process known as increasing metamorphic grade. This type of metamorphism records the tectonic history of a region and is crucial in the formation of mountain belts and continental crust. Plutonic metamorphism. The rock shown is produced by plutonic metamorphism, which is a coarse-grained, deep-seated metamorphic rock formed under high temperature and pressure in deep crust. Plutonic metamorphism occurs deep within the Earth's crust, typically beneath regional metamorphic zones, where rocks are exposed to very high temperature and pressures for extended periods. Unlike other types of metamorphism, deformation is minimal. In this environment, instead, rocks experience static conditions, allowing equilibrium mineral assemblages to form, meaning minerals grow and rearrange themselves in a stable, balanced way without much stress or movement. This results in the formation of coarse-grained metamorphic rocks, which are marked by large, well-formed mineral crystals and stable mineral structures. Plutonic metamorphism is often seen as a high-grade extension of regional metamorphism, representing the deepest and the most intense metamorphic conditions. It plays a key role in the forming the rocks of mountain belts and stable continental interiors. The image depicts metasomatism, showing mineral replacement within a rock mass due to infiltration of chemically active fluids. The image highlights contrasting mineral zones, distinct color changes, and textural variation, representing the chemical alteration process without melting. Metasomatism is a metamorphic process where the chemical composition of a rock is altered due to the interaction with chemically active fluids such as aqueous solutions, vapors, or gases. Metasomatism can be classified based on the nature of chemically active fluids involved. Hydrothermal metamorphism. This occurs when rocks are altered by hot iron-rich aqueous fluids, typically originating from cooling magmas or deep groundwater systems. These fluids facilitate chemical reactions that forms new minerals and change the rock's composition. It is common near mid-oceanic ridges, igneous intrusions, and geothermal regions. New metallitic metamorphism. This involves chemically active gases or vapors such as fluorine, chlorine, and boron, usually released during the late stages of magma crystallization. These gases react with surrounding rocks, promoting mineral changes at relatively high temperatures. For civil engineers, understanding metasomatism helps in evaluating rock integrity and performance in fluid-rich or geothermally active zones. Shock metamorphism. The image depicts a close-up of rock altered by shock metamorphism, showing fractured and shattered texture formed under the extreme pressure from a sudden impact event. Shock metamorphism is a rare but dramatic type of metamorphism that occurs when a meteorite or asteroid strikes the Earth at extremely high speed. This sudden impact generates instantaneous high pressure and temperature, far exceeding normal geological processes. The intense energy of the impact transforms minerals in unusual ways. For example, quartz can convert into high pressure forms such as coesite and stishovite, minerals not typically found in Earth's crust. Shock metamorphism also produces distinctive geological features including shatter cones, cone-shaped fracture in rock pointing towards the impact, planar deformation features, microscopic shock-induced structure in quartz, impact breccias, broken and re-cemented rock fragments formed during the collision. These features are found in and around impact craters and ancient eroded impact sites, helping scientists identify past meteorite impacts and study planetary processes. Structures of metamorphic rocks. Metamorphic structures are the distinct physical features formed within a rock due to the intense heat and pressure it has experienced during metamorphism. They reflect the shape, arrangement, and interrelationship of mineral grains. These are of the following types: cataclastic structure, maculose structure, schistose structure, granulose structure, gneiss structure, xenoblastic structure, and ideoblastic structure. Cataclastic structure. Image shows a cataclastic structure characterized by angular rock fragments embedded in fine-grained crushed matrix. The fractured and broken pieces indicate intense mechanical deformation, with some fragments fitting together like a jigsaw, suggesting brittle failure under high stress. Cataclastic structure results from intense mechanical deformation, typically along fault zones, where rocks are broken into angular fragments and embedded in a fine-grained crushed matrix. Soft rocks, example shale, tuffs, may develop cleavage under stress. Harder rock becomes progressively fractured, fragmented, or pulverized, showing brittle failure. Maculose structure. The image shows a metamorphic rock with a maculose structure featuring a fine-grained dark matrix scattered with numerous circular to oval spots. These spots or maculae vary in size and are typically a darker greenish gray, creating the rock's distinctive spotted appearance. Maculose texture is a type of metamorphic rock texture characterized by a fine-grained, darker matrix speckled with distinct circular or oval spots. These spots, called maculae, are typically composed of large mineral crystals or fibroblasts like chloritoid, which grew within the finer matrix. The presence of these large crystals create a characteristic spotted appearance that is a key identifying feature of this texture. Schistose structure. The image shows a metamorphic rock exhibiting schistose structure characterized by parallel alignment of platy and flaky minerals. The layers appear thin and continuous, giving the rock a distinct foliated appearance. Such structures are developed due to the alignment of platy or flaky minerals like mica, chlorite, and talc, imparting a foliated or layered texture, typical of schist and indicates a high degree of metamorphism. Granulose structure. The image shows a metamorphic rock with a granular, non-foliated structure where minerals such as quartz and feldspar are tightly interlocked in a mosaic-like pattern. The crystals are equidimensional and lack any preferred alignment, reflecting formation under high temperature conditions. Granulose structure consists of an interlocking mosaic-like texture of roughly equal-sized granular minerals such as quartz and feldspar. It typically forms under high temperature conditions where minerals recrystallize without significant directed pressure. This results in formation of a non-foliated rock fabric, a key characteristic of rocks such as marbles and quartzite. Gneiss structure. This image shows a metamorphic rock with gneiss structure characterized by alternating dark and light mineral bands, coarse texture, and well-developed foliation formed under high temperature and pressure. In gneiss structure, minerals are segregated into alternating light bands of quartz and feldspar and dark bands of biotite or hornblende. It develops under intense heat and pressure during regional metamorphism, often in deep crustal conditions. The rock shows a coarse-grained texture with minerals aligned in parallel layers, producing a distinct banded appearance. Xenoblastic structure. The image shows a metamorphic rock with xenoblastic structure characterized by irregular interlocking mineral grains lacking well-defined crystal faces due to mutual interference during recrystallization. Xenoblastic structure forms when minerals grain lack well-formed crystal faces due to mutual interference during growth. It develops during solid-state recrystallization under restricted space conditions. It is common in many metamorphic rocks, indicating intense pressure and strong mineral interlocking. Ideoblastic structure. The image shows a metamorphic rock with ideoblastic structure where mineral grains possesses well-formed crystal faces indicating growth without significant interference from neighboring minerals during recrystallization. Ideoblastic structure is characterized by minerals displaying well-developed crystal faces even within a solid rock matrix. It forms when crystals grow freely during metamorphism, allowing them to preserve their natural crystallographic shape. This structure suggests minimal interference from surrounding minerals during growth, indicating favorable space conditions for crystal development. Textures in metamorphic rocks. Textures in metamorphic rocks provide important clues about how the rocks were formed. The texture describes how the mineral grains are arranged and relate to one another. Main types of texture in metamorphic rocks are foliated texture. Minerals are aligned due to compressional forces. These bands or layers are characteristics of regional metamorphosed rocks like slate, schist, and gneiss. Non-foliated texture, on the other hand, results when pressure is uniform or when the minerals do not show a tendency to align. This occurs in contact metamorphism, producing rock-like marble and quartzite. Granoblastic texture is a subset of non-foliated texture where equidimensional grains grow in interlocking mosaic pattern, typically under static high-temperature conditions. Porphyroblastic texture are unique in that large metamorphic minerals, porphyroblasts like garnet, grow within a fine-grained matrix. Cataclastic texture is a result of mechanical breakage of minerals due to intense stress, usually along fault zones. The rock appear crushed or fragmented. These textures not only help in classifying metamorphic rocks but also reveal details about the pressure, temperature, and deformation history a rock has experienced. Classification of metamorphic rocks. Metamorphic rocks are classified primarily based on their texture and composition, which reflect the condition under which they are formed. These textures are influenced by temperature, pressure, deformation, and mineral composition. The main types are foliated metamorphic rocks, non-foliated metamorphic rocks, cataclastic metamorphic rocks, impact metamorphic rocks. Foliated metamorphic rocks. The first major category is foliated rocks, where minerals are aligned in bands due to the directed pressure during regional metamorphism, giving the rock a stripped or platy appearance. This develops due to directed pressure causing platy and elongated minerals like mica or chlorite to align perpendicular to the maximum stress. Common in regional metamorphism, these rocks show a clear progression in metamorphic grade. Slate is the lowest grade with microscopic grains. Phyllite has a silky luster and slightly larger grains. Schist has visible platy minerals like mica. Gneiss has distinct light and dark banding due to segregation of mineral types. Non-foliated metamorphic rocks. The second category includes non-foliated rocks which form when pressure is equal in all directions or when the mineral makeup does not allow foliation. Minerals are randomly arranged with no preferred orientation, often forming under uniform pressure or in rocks composed of equidimensional minerals that do not align easily. Typically found in contact metamorphism, these rock types include marble formed from limestone composed mainly of calcite, quartzite formed from sandstone, very hard and resistant, hornfels, a fine-grained rock formed in contact metamorphism zones, anthracite, the highest grade of coal. Cataclastic metamorphic rocks. These rocks, derived from various protoliths, typically found in fault zones, exhibit crushed, fragmented or sheared texture formed by intense mechanical deformation and shear stress, reflecting grinding and breaking rather than thermal alteration. These include fault breccia, broken rock fragments cemented together, myelinite, finely foliated, formed by intense ductile shearing. Impact metamorphic rocks. Derived from quartz-rich rocks, these shock metamorphosed rocks form under extreme impact conditions, displaying deformed texture and high-pressure minerals. These include coesite and stishovite, high-pressure forms of quartz, impact breccia, fragments formed by shattering and melting during impact. Identification of metamorphic rocks. Foliated. Rocks displaying layered or banded texture, form from shale, slate, phyllites, or granite, and exhibit mineral alignment due to directed pressure. Example include slate, phylite, schist, and gneiss. Non-foliated, having granular or massive texture, originate from limestone, sandstone, shale, or coal, and lack visible foliation. Examples include marble, quartzite, hornfels, and anthracite. Cataclastic, exhibiting crushed or fragmented texture, forming in fault or shear zones due to mechanical deformation. Examples include fault breccia and myelinite. Impact or shock type. These rocks have a shocked or deformed texture typically derived from quartz-rich parent rocks and form unique high-pressure minerals due to meteorite impacts. Examples include coesite, stishovite, and impact breccia. Self-assessment questions. At the end of the presentation, these are self-assessment questions. Go through each question carefully. Answer these questions based on understanding of the topic. Review any concept you are unsure about. The questions are: define metamorphic rock. How are they formed? And what roles do heat, pressure, and fluids play? Explain the types of metamorphism. Mention conditions, agents, and typical rocks formed. Describe major structures of metamorphic rocks. Give characteristics, conditions, and examples. Explain major texture of metamorphic rocks. How do they reflect pressure, temperature, deformation history? On what basis are metamorphic rocks classified? Explain foliated, non-foliated, cataclastic, and impact types with examples. Discuss the effect of metamorphic structures on rock stability. Give examples of rocks suitable or unsuitable for construction. Thank you for joining this lesson on engineering geology today. Hope you found this presentation informative. So don't forget to like and subscribe the channel Dr. A Classes for more engaging lessons on core subjects of civil engineering. Thanks.